using the iPad because our phone has broken. And here we are. Here is Baji. Baji wants to say hi. Baji wants to say hi. Baji wants to say hi. Who is ready to say hi to Baji? Baji wants to say hi. Hello. So we got your comments from yesterday's live. Some of you have been very encouraging about the phone breaking situation. And you said that the iPad was just fine, which we're very grateful for. Thank you. Hello, Annie Frank. How are you? Annie says, hello, everyone. Hello. Here is Baji, Fuji, Suji, and me. I'm here for the antics. Indeed, there were and sometimes are antics on the channel. Currently, we are using this iPad to go live because my phone has broken. But Baji wanted to say hi as we still kind of decide which phone to get next. And in fact, if you have any suggestions, those are most welcome. Welcome to the live. Welcome, welcome, welcome. Hello, 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 hello. Welcome to the live. If you can hear me all right, say hello. If you want to say something in the chat, say hello and say it, and I will read your comments. Wade says, what are we talking about today? Wade, hello. What do you want to hear about, Wade? We generally talk about astronomy, cosmology, astrophysics. Molly! Hey, Molly says, hey. Hello, Molly. Why'd you break your phone? Well, I dropped it while using Google Maps, so that's how it broke. Baji wants to say hi though, so we're using the iPad to go live. And welcome to everybody. Welcome to the USA, welcome to UK, welcome to all of the continents, Antarctica, South America, Africa, Europe, Asia. Who is here? Who is here? Dora told me you guys talk about physics and some dude called. Yep. Do you think something is hidden on the dark side of the moon? Oh, that's a great question. Something hidden by us, human beings, or something from what, just naturally. We did talk about the moon quite a bit on this channel, actually. We saw how the moon formation's history and our history as Earth are kind of different. The moon and the Earth are kind of different historically. We talked about how the moon may have been formed, and talked about a few different theories, and the most likely one being that we might have collided with a planetoid and absorbed part of its core, making us and our core more enriched, and then part of the surface of the Earth kind of ejected out as the moon, and therefore the moon's surface and our surface and our general compositions are quite different. The moon does not have an iron core like us. The moon's density is different. The moon's surface is older and has less diverse types of things than we do. And the moon, of course, does not have an iron core. And the moon does not get volcanoes. So it still has preserved sort of an older surface, which involves impact craters. We talked about the era of heavy bombardment in our solar system when we had, basically by the bombardment of these planetesimals onto all of us, planets and moons and everything, we basically ended up with cratering, heavy cratering. And because the moon's surface did not get paved over by volcanoes like we have paved over our surface here on Earth, it actually retains some of those old features and old characteristics. And in that sense, it's an older type of surface. Older rocks are possible to be collected from the moon. And when we did land on the moon, through our space missions, we did bring back a bunch of rocks. So those are some tidbits about the moon. Do you think something is hidden on the dark side of the moon? Asked Wade. Well, we couldn't have hidden anything there, says Annie Frank. Some people don't believe that we landed on the moon. In fact, we did. We did land on the moon, and we did bring back a lot of rocks. And you can find more information about that. We spoke about those rocks briefly on this channel at one point. Do you think there's something being kept from the public there? I don't. I mean, I'm not a big conspiracy theorist. So I don't think there is anything hidden on the moon, but you know, I'm open to a discussion on it. And if you want to share any thoughts or concerns about why you think there may or may not be something hidden on the moon, then let us know in the chat. Annie Frank says correct. When will we change? If you declare with your time is short. Okay, hi Tarek. Hello everybody. Welcome to the live. Hi Barbara. Barbara, thank you so much for your emoji. Wade, thank you for your questions. Keep on asking more. Let us know what. Oh, can everybody please like the live? That would be amazing. Thank you for your questions one more time. Wade, Annie Frank, when will we change? Tarek, and Elon Musk with his billions can't even go up a few miles, but you want us to believe. Yes, it did happen in the past, quite a while ago. I heard a story that the American government gave a meteorite to a foreign country, possibly Denmark, that turned out later to be just a rock from Earth. Okay, that's new to me. It's interesting what people are sharing on the chat. Keep them coming. Love it. Keep them coming. Love it. Love it. Love it. So that's awesome that people are interested in the moon so much. That is, I have been summoned. Hello, Doro. Here you are. How are you? We are, once again, welcome everybody to the live. We are going live using our iPad because the phone has broken. I am finalizing exactly what phone I'll get next. So, okay. Doro, hello, and Doro, see you later. Get you the new iPhone. Yep, I wish. I only get used phones actually. So I'm looking at used, renewed, unlocked, works well kind of phones. I don't like to pay full price for a new phone, so I'm gonna go with some older model, which is hopefully heavily discounted and still works. So yeah, that's the plan. Apple refurbish rules. Yeah, I get refurbished phones on Amazon, but yeah, that's the idea. I'll trade mine in. It still kind of works, the phone. It's just very unfortunate because I wasn't really trying to buy a new phone right now. I was hoping that this phone would last forever and keep on going. I know the quality of the phone is not the best. It's not got the newest technology, but I thought it was still working. And if it didn't break, I would probably just keep using it. But maybe I'll get myself a slightly newer technology phone, and maybe you guys will get to enjoy a slightly better experience of the video qualities and stuff. So hopefully it's it works out. Oh, and I completely forgot to clip this. I forgot to clip it. All right, they get their food has fallen, so Mama's gonna go and help out Suji here because seems like she is waiting to be helped. Here, Baji, why don't we have you use this one and you take this one, because Baji likes to eat from the slow bowl. He likes a challenge when it comes to the food. Hello, crazy sick one. How are you? Beautiful cats, though. Thank you. To be fair, I'm not suggesting it proves we faked the moon landing, just a funny story. Yes, I follow. I think I understand what you're saying. That it is another sort of entertaining story or thought or something like that. Rick says, oh, thank you, Amanda. Thank you. Beautiful cats, though. Thank you. Rick Flair says hi. Hi, Rick. Crazy Sick One says, how are you feeling today? I'm good. I'm good. Just sad about my phone, but I'm good. How are you? You should stop by my live kittens. Sometimes they're almost a week old. Oh my gosh. Will do, Amanda. Love it. Love the profile picture as well. Thank you so much for coming to the live. Dora says, okay. Yeah, Dora, you feel free to go back to work. That sounds great. Milky Way says hi. Oh, whoops, I stepped on a bone. Sorry, Baji. I'm sorry. I'm not doing anything. I'm so sorry. For what reason, though? What's to gain? What's to gain from what? What are you asking about? Ooh, can we please get 10 likes? Thank you so much. Thank you, thank you, thank you. Look at this. I even have this phone charger. I can see it on the iPad. The iPad's video quality is definitely a little bit not the best, but it's working. It's something. Dora says, oh yeah, you're asking why we would have faked it. That's a great question. Can we get 10 likes? Thank you so much. For what reason? Dora is kind of trolling. He is a regular on these lives, and he is in fact a moderator, but sometimes he could very well use some moderation himself, because he just jumped in just to kind of you know, be funny, I guess. And that's why he's saying that. I don't think he believes that we did not land on the moon. I think he's just kind of saying that. To be fair, I texted Dora. That's fine. That's fine, Annie Frank. Love it. Dude's been crazy busy. Wow. He made time for us. He has made time for us. Thank you, Dora. Yeah. Okay. Wow. Lots of corporate busy people coming into the live just to make time for us. Death Dragon! Oh my gosh! Hello! Where is Death Dragon here? I haven't heard from him in forever. My friend Death Dragon told me about you. I'm an old friend. That's how I got here, and I think you know him. Yes! Of course I know Death Dragon. He has been a mod as well. I'll stay here and hold the line. Thank you, Annie Frank, for your kind presence, I suppose. It's a pleasure, sort of. Death Dragon is a young friend of the channel. So yeah, he was a mod and he banned almost everybody at one point. So I think his help is sort of almost a little wild and a little intense, but yeah, it was great. Let's see. Crazy Sick Wine says, I'm doing chilling. Great. Awesome. Thank you, everybody. We will start some topic and talk about things. Can everybody still hear me? I gotta go grab my book actually from the other room. Let me do that. Okay, so it's interesting somebody asked about the moon today. Maybe we will talk about the moon, maybe we'll talk about some other moons. I think we have actually talked about the moons of our solar system quite a bit, including, of course, the giant moons of the solar system. There are 7 of them. We have one. So the moon of Earth is one of the giant moons. We've also talked about the Galilean moons of Jupiter. We've also talked about Saturn's Titan and Neptune's Triton. So if you're interested in the moons of the solar system, indeed we have spent quite a bit of time on it actually. So if you catch our other lives, if you go onto the live tab of my channel and look at the other lives that we've done, hopefully some of them I've actually named appropriately and let people know that I'm going to be talking about the moon and such. But yeah, I'm hoping that you can find much more information about the moons of our solar system from these other lives that we did already. Triton, satellite of Neptune, is something we spent some time with as well. It's a sort of a anomaly, I think that's the right word, anomaly of a moon. It has a retrograde orbit, and we talked about how it may become one of the rings of Neptune as it's getting closer and closer, and its orbit is actually becoming smaller. So things like that are definitely things we have covered from an astronomy point of view. Of course, I'm not so sure about the political views about our moon, for example. Maybe those things are things as well, but I'm unaware because it's not really my interest. But you are welcome to share your comments on such things as well. So next, I think, let's see. We have also talked quite a bit about the history of the universe. And indeed, we have talked about it from a cosmology point of view, and also mentioning things like the Big Bang, the early universe, the evolution of the universe, the smooth universe, the perturbations to the smooth universe. Now, we didn't cover too much details on the perturbations to the smooth universe because I'm still figuring out a digestible form or format for delivering that particular material. But we did take a look at cosmic inventory, cosmic ingredients, things like that too. So I sort of mentioned generally what we cover on the channel almost every live so that people who are kind of joining get a feel for it and understand what sort of things we're covering here, so that you can always go find the older lives if you are interested. Let me get the iPad over here. It's a little bit difficult to carry around, but here it is. Oh, you know what? Maybe I can just put it like this over here. Maybe it can be standing sort of like this. And then you can still see Baji. Look at that. Wow. 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 Nice. Okay, could we get 10 likes, please? Thank you so much. Really appreciate you. Can we get 10 likes? Can we get 10 likes? Thank you. Thank you. Ah, there is Suji Mama and Baji Baba. I think someone said that I'm a cat tuber who talks about astronomy and cosmology, or I'm an astrophysicist who shows cats. So either one is true. Whichever resonates more with you, you're welcome to join. Welcome to the live. Welcome. Wow. Also, let me share the live. I never did that. Thank you everybody for being here. Welcome. Please do like the live. Thank you. I think we will cover some, oh no. Something happened where I wasn't able to click on my live, actually. I'm trying to share it from my other device. So give me 1 second. Thank you. Thank you for liking the live. Can we get 10 likes? Thank you so much. And oh, you know what? The title is wrong. I think I have an extra hashtag there. which is fine. Indeed, that is fine. Indeed, that is fine. Oh, let me see your comments. Sorry. The comments disappeared too quickly on the iPad, but I'm looking at them on my computer now. So let me see. Let's see. Milky Way says, can I go get him? He might not look different because we have the same profile. Yeah, go for it. Nice cat, says John Foster. Thank you, John. He's sleeping, never mind. Aw, thank you. Crazy says, very good, very good. Okay, very good. So you're doing well. Capri on the wall there. You've been to Greece. I have not yet. I have not actually been to Capri yet. I'm hoping that I go there soon, though. It's I'm trying to manifest it by putting it on the wall. I have not yet been to Greece, but or other parts of Italy that I want to go to. And yeah, not been there yet. Not yet. It's a goal of mine. He is really, really feisty, like really cranky when he just doesn't get the right amount of sleep. The Milky Way, I love your username. We have also talked about the Milky Way quite a bit on the channel, so thank you so much for joining. Hopefully, if you like the Milky Way, you will find a lot of content in the older lives on that as well. You have a lovely face, you show on occasion. Thank you. Brilliance is upon thee forevermore. Oh, thank you, thank you, thank you. Thank you. Any astronomy questions? Thank you so much, everybody, for being here. We are doing the Kitty Cat Live, and we might also answer your astronomy questions, and we're also catching up with everybody in real time. So thank you, everybody, for being here. Hello. Oh, wow, it's 444. No, it just turned 445. He is zonked out. I can't even wake him up, and he is also really heavy sleeper. I just wanted to see the wild chat. Made a very bad typo. I want to talk of the cataclysmic events that have led to the human 16. You want to talk about the cataclysmic events that have led to the human demise of the failure of our virtue. I'm not sure what that means, but can we get 20 likes, please? Hi, Rick. I don't know how he thinks I'm rich, but thank you. Get the most expensive phone. Dora said you're rich. Who wants to sponsor the phone? Who? Google, feel free to sponsor a phone. Apple, feel free to sponsor a phone. Sponsor the phone. I'll give you a quarter. Okay. Sounds good, I suppose. I think that being able to take up space on this live is worth more for you, but that sounds good. Ric Flair says hi. Hello. Samsung! Samsung, give this lady a phone. Wow. Phone time. Send phone. Thank you. Thank you. Kitty Monster 3000 says hi. Rick says hi. Hi, Rick. And hi, Kitty Monster. Hello. Hello, hello, hello. What is an astronomy question you have? I will pin that. I will pin this message. Yay. Remember the good old flip phones of the early 2000s, of course. Of course I do. Yes, indeed. I have a science question actually. Hello, glad to catch you today. Hi. Hello, not just cats. Thank you, Yeshua. Love it. Thank you so much. Hi. I have a science question. Why did not we? Well, we did. We did. We did. Thank you, Annie. We did. Indeed, we did. We can again. Thank you for liking the live. Thank you so much. Really appreciate it. Thank you, thank you, thank you, thank you, thank you, thank you. Milky Way, love that emoji. Thank you so much. Okay, let me real quick cover something interesting and then we can be on our way. Molly, are you still here? Apple, iPhone 16 possibly. Is that the one you think I should get? I think I'm gonna get something renewed though. Something used. Hi, Fuji baby. Let me show you Fuji in just a second. He's being so funny. Something used. Hi, Fuji baby. Look at Fuji baby. Fuji. He's doing tricks and he's giving us tips and tricks. He's all the way up in the ceiling now. He's up in the ceiling. Fuji baby, you're such a cutie. The biggest cutie of all. Evil eye remove. Thank you, universe. He's the biggest cutie of all. Thank you, thank you, thank you. Fuji has gone up there and he was like looking at the ceiling and talking to it. He is such a talkative baby. He's a baby. Oh, and here is Sachi Mama. Here is Sachi Mama. She hunted a bug yesterday at night. Oh, she's so cute. Thank you. Thank you. If Death Dragon was here, would he be? Of course. Death Dragon is welcome. What do you mean? He has always been welcome. Death Dragon, don't be shy. I wish I could do that. Can't in an apartment. One meeting is enough for me. Oh my goodness. Is the universe truly infinite? I have 3 kitties too. So lovely. Thank you. Why did Dora tell me you couldn't understand English? That could be. Do you work with Dora in the same office? Where art thou, Death Dragon? The stuff on the walls, you know. Yes, yes, yes. The shelves, yes. Oh, Fuji's coming to Mama's lap. Or not Fuji, Suji's coming to Mama's lap. Suji, here is Mama's lap. Oh, look at Suji. She came to Mama's lap. That's why she's not in there. I work around him. We don't work for the same organization. There is a wall of galaxies at the end of the universe. Also, there is nothing, so it is not infinite. You see Dora and Grimmy all the time? Wow. Goodness. Goodness, goodness, goodness. Look at us. All real life people. So we can talk about the universe being infinite / flat real quick, actually. That is a very important. In fact, didn't someone ask about the end of it? Not that this is something we have to, I don't know. Not that this is something in this exact language that we have to. I'm looking something up. 1 second. I want to cover something that I thought of just now. I'm looking it up. Let me. In the meantime, can someone say who discovered the moons of Jupiter first? Question for you. I'm looking something up on the index, and it is a little bit. Wow. Galileo, yes. So here we go. Here, oh gosh, that's my finger right there, my hand. So in a strictly Newtonian universe, oh, Fuji has come down. Look at this. Fuji has come down, and Fuji wants lap time now. Fuji wants lap time. Hello, Fuji. Hi. Galileo Galilei. Galileo Galilei. Indeed, that's a great answer, Annie Frank. Indeed. So in a strictly Newtonian universe, the fate of the universe, big crunch or big chill, is determined solely by the ratio of the average mass density to the critical density. So we have not talked too much about the big crunch or big chill, but let's just see what the authors have to say on this right here, right now, sort of without too much introduction. We can always come back to this topic in more detail later on. But apparently it's all going to be about the ratio of the average mass density to the critical density. However, if a cosmological constant is present, remember that dark energy is basically, it got started with the cosmological constant about 100 years ago when Einstein was doing the equations for the universe with his general theory of relativity. If a cosmological constant is present, then this ratio of densities no longer uniquely determines the ultimate fate of the universe. A cosmological constant is an entity that provides a positive acceleration. So if acceleration is A, or sorry, if position is A, then A dot dot, double derivative of the position is going to be acceleration. So it provides a positive acceleration to the expansion of the universe. If there is cosmological constant, more generally called dark energy. The cosmological constant was introduced by Einstein in the context of general relativity. So we know this because we covered this in an earlier live, but here's a little bit of a review for you. Since the Newtonian view is that gravity is always an attractive force, it will be necessary for us to dabble in general relativity in order to understand the cosmological constant and the possibility of an accelerating universe. Wow. In Newton's view of the universe, space is static. In Newton's view of the universe, space is static, unchanging, and Euclidean. In Euclidean or flat space, all the axioms and theorems of plane geometry, as codified by Euclid around 300 BC, hold true. In Newton's view, an object with no net force acting on it moves through this Euclidean space with a constant velocity. However, when we look at real celestial objects, comets, planets, asteroids, and so forth, we find that their velocity is not constant. They move on curved lines with continuously changing speeds. Why is this? Newton would say their velocities are changing because there is a force acting on them, the force called gravity. Newton derived a useful formula for computing the gravitational force between two objects, Every object in the universe, said Newton, has a property that we may call the gravitational mass. Let the gravitational mass of two spherical objects be small mg and big mg, and let the distance between their centers be r. The gravitational force acting between the objects is given by negative capital G mg mg, the two m's over r squared, where this capital G is the Newtonian gravitational constant. We often mention it. It's a good thing we're defining it out here because this often comes up in all kinds of gravitational type of things. The gravitational mass of an object is a non-negative number. Hi, Milky Way. Hi, Crazy Sick Wine. So the Newtonian gravitational force is always attractive with an F gravity of less than or equal to 0. Newton also provided us with a useful formula that tells us how objects move in response to a force. Every object in the universe, said Newton, has a property that we call the inertial mass. If the inertial mass of an object is mi, then if a net force F is applied to it, Newton's second law of motion tells us that this acceleration will be A equal to F over mi. So I think you guys know all this already. This is just a little bit of a review. And guess what? The small mg that we just now talked about in the earlier gravitational force equation and this inertial mass, turns out that those two are actually equal. One of the fundamental principles of physics, a rather remarkable one if you stop to think about it, is that the gravitational mass and the inertial mass of an object are identical. mg is equal to mi. The equality of gravitational and inertial mass is known as the equivalence principle. The gravitational acceleration A of an object under the influence of a sphere of mass big mg will generally be given by that F gravity number divided by mi. And if the equivalence principle didn't hold true, then different objects would fall at different rates in the Earth's gravitational field. I'm totally lost, but this is okay. So this is just Newtonian mechanics. Hopefully, if you can always rewind and hear it again. And Newtonian mechanics or classical mechanics is something we didn't cover too much because it's a very old classical physics that I think most people know and whatnot. But thank you. I'm totally lost. Have a very wonderful day. You too. Thank you. Thank you for coming. So if the equivalence principle, this inertial mass being equal to the gravitational mass, is actually extremely important, because if this was not the case, then A would not equal to the rest of that stuff that we just talked about, the F gravity over mi, and it would make it so that different objects would fall at different rates in the Earth's gravitational field. The observation that A is actually a constant given this planet, for example, on Earth it's negative 9.8 meters per second squared for all objects near the Earth's surface, is supporting evidence that the equivalence principle holds true. How interesting is that, guys? How interesting is that? I'm going to make a note, actually. You know what? I will teach this topic again using a whiteboard or a chalkboard. I think that will help. Because Newtonian mechanics is not very difficult. I think if you saw it, you would understand it very easily. Okay, so it is the equivalence principle that led Einstein to devise his theory of general relativity. So general theory of relativity is the updated, more correct theory of gravitation, and Einstein worked on it about 100 years ago. And it's really nice because it works and gives us corrections to classical mechanics that are important when we consider larger scale and things going at close to speed of light and whatnot. It's a more general theory of relativity that he was inspired to work on after he finished his special theory of relativity. Hi, Fuji. Hi, thank you for Thank you. Let me put this over here so that I'm not disturbing the live too much. You can look at Suji and I can keep talking about the physics here. So in this equivalence principle, this inspired Einstein to work on his general theory of relativity. And here's a thought experiment that we can talk about in a moment here. Let me share the live again. Let me share it again. Are we going to explore different galaxies? Do you mean in general, like in science, or on this live? We did talk about different galaxies in the live earlier. That's a great question. Let me know which type of galaxy are you wanting to learn more about? Is there a type? Okay, so we will now look at a thought experiment with the general theory of relativity. Suppose you wake up one morning to find that you have been sealed inside a small, opaque, soundproof box. Great. Suppose you wake up one morning to find that you've been sealed inside a small, opaque, soundproof box. So it's small, it's opaque, as in you can't really see through it. Soundproof, you can't really hear much from the outside coming through. You're so startled by this, you drop your teddy bear. Observing the falling bear, you find that it falls towards the floor with an acceleration of minus 9.8 meters per second squared. Will, you say with a relief, at least I'm still on the Earth's surface and not being abducted by space aliens. At that moment, a window in the side of the box opens to reveal that you are in an alien spacecraft that is being accelerated at an A of 9.8 meters per second squared by a rocket engine. When you drop a teddy bear or any other object in a small sealed box, the equivalence principle allows two possible interpretations. The bear is moving at a constant velocity, and the box is being accelerated upward by a constant non-gravitational force, or two, the box is moving at a constant velocity, which may be zero, and the bear is being accelerated downward by a constant gravitational force. The observed behavior of the bear is the same in each case. So once again, the bear could be moving at a constant velocity, and the box is the one that's being accelerated upward by a constant non-gravitational force, like, for example, a rocket engine accelerating it. Or the box could be moving at a constant velocity, which may be zero, and the bear is being accelerated downward by a constant gravitational force. So those are the two things that could be happening, and the observed behavior would be the same in each case. Now, suppose you're still in the sealed box, being accelerated through space by a rocket at A equal to 9.8 meters per second squared. So you're accelerated by a rocket, and your acceleration is 9.8 meters per second squared. You grab the flashlight you keep on the bedside table and shine a beam of light perpendicular to the acceleration vector. Since the box is accelerating upward, the path of the light will appear to you to be bent downward toward the floor, as the floor of the box accelerates upward to meet the photons. So again, since the box is accelerating upward, the path of light will appear to you to be bent downward toward the floor, as the floor of the box accelerates upward to meet the photons. However, thanks to the equivalence principle, we can replace the accelerated box with a stationary box, experiencing a constant gravitational acceleration. Since there's no way to distinguish between these two cases, we're led to the conclusion that the path of the photons will be curved in the presence of a gravitational field. Gravity affects photons, Einstein concluded, even though they have no mass. Wow. And why is that? Because, so, you know, spoiler alert, gravity bends space-time. So, and since photons will move in space-time, photons can get curved due to gravity, okay? So gravity affects photons, Einstein concluded, even though they have no mass. So having mass is not necessarily needed if you want to be affected by gravity. Contemplating the curved path of the photons, Einstein had another insight. A fundamental principle of optics is Fermat's principle, which states that light travels between 2 points along a path that minimizes the travel time. Wow. Wow, 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 wow. In a vacuum where the speed of light is constant, this translates into the requirement that light takes the shortest path between 2 points. In Euclidean space, the shortest distance between 2 points is a straight line. In the presence of gravity, however, the path taken by light in a vacuum is a curved line. This led Einstein to conclude that space is actually non-Euclidean. It's not flat and Euclidean, but it may be, just maybe, non-Euclidean. The presence of mass in Einstein's view causes space to be curved. More broadly, in the theory of general relativity, mass and energy, which Newton thought of as very different things, are interchangeable via the equation E equals mc squared. Moreover, space and time, which Newton thought of as very different things, form a four-dimensional space-time. A more complete summary of Einstein's viewpoint, then, is that the presence of mass energy causes space-time to be curved. This gives us a third way of thinking about the motion of the teddy bear in the box. No forces are acting on the bear. It is simply following a geodesic in curved space-time. The word geodesic in this context is shorthand for the shortest distance between 2 points. In general, computing the curvature of space-time is a complicated problem. Since the distribution of mass and energy is inhomogeneous on small scales, the curvature of space and time is also inhomogeneous, with strong curvature near black holes and neutron stars and weak curvature in intergalactic voids. So once again, computing the curvature of space-time is a complicated problem since the distribution of mass and energy is inhomogeneous on small scales. The curvature of space and time is also inhomogeneous with strong curvature, lots of curvature of space-time, lots of bending of space-time near black holes and neutron stars, which are massive objects, very, very much more massive objects than usual other objects, and weak curvature, weaker, lesser bending of space and time in intergalactic voids where there is less massive things. However, on scales bigger than 100 megaparsecs, this is a bigger distance, more like an intergalactic kind of distance. On scales bigger than 100 megaparsecs, the spatial distribution of mass and energy appears homogeneous and isotropic. So when you go farther out, when you zoom out more to the point of 100 megaparsecs, which is the distance within which there could be a ton of galaxies, then the spatial distribution of mass and energy appear more homogeneous and isotropic. So it's really at a smaller scale that you find the inhomogeneity. So now when we go zoom out, more homogeneous, more isotropic. Thus we conclude that the curvature of space is also homogeneous and isotropic on large scales. The assumption of homogeneity and isotropy vastly simplifies the problem. There are only three basic geometries that space can have under such restrictive conditions. Since picturing the curvature of three-dimensional space is difficult, we'll start by considering the curvature of two-dimensional spaces whose pictures can be neatly drawn on paper. Later, we'll generalize to three dimensions. Thank you, Amanda. Thank you. Love the emojis. Thank you, Milky Way. Thank you, Crazy Sick Wine. First of all, space could be flat, Euclidean. So we're just imagining it. It'll turn out that we need to be non-Euclidean later on. But we could say that space is Euclidean for the moment. Thank you, random guy. How are you doing? So this chapter, that's from this book, by the way, is sort of a review of the stuff that we've covered already in the past when we talked about cosmology. In the past, we talked about Einstein's equations. I think that was one of the titles of our lives. So we talked about that, this sort of stuff already. But it's nice to be able to review this. So the next parts are more mathematical, so I'm trying to find a good spot to keep going on the material. So we talked about the metric earlier, and there's a review of that here as well, which is nice. Ooh, and we're gonna do the Friedman equation math here. You know what? As soon as I get a whiteboard, I will do this for you. Let's talk about the cosmological constant really quickly. Now, Seth, how are you? So there will be some math that we discussed. If you are interested, the stuff that I'm skipping today, I covered under Einstein's equations in a previous live. I want to cut to the spot where we talk about the cosmological constant from this text because they explain it a little bit different. It's the same stuff, but I think it's worth reviewing because it's such an important topic. And we were just now talking about about the universe here. Milky Way is back. I was gone because I was eating. Thank you for liking the live. Thank you. Milky Way, Death Dragon, how are you? Nasath, how are you? Amazing Amanda, how are you? Random Guy, how are you? Very nice. Love it. So, in going from the Newtonian to the relativistic form of understanding gravitation, because we can understand gravitation in a Newtonian way, that stuff that I was talking about with the GMM over R squared and all of that, where the inertial mass turns out to be equal to the gravitational mass, all of that is fairly simple. It's the Newtonian mechanics way of doing things. But then remember, Einstein was inspired to give us a more correct theory of gravitation with his general theory of relativity, where we consider basically massive objects to be able to bend space and time, and gravitation is more of a curvature of space and time. And so there's more curvature near more massive bodies like black hole and neutron stars, and less curvature near in the intergalactic medium or in intergalactic voids. But then we talked about how when you go more large scale, at a scale of around 100 megaparsecs, you see that these everything is more homogeneous and isotropic, and the inhomogeneities are really seen at a smaller scale. Oh, Suji's taking care of Fuji and herself. So now we will talk about the cosmological constant, which is often denoted by the Greek letter lambda. It's a capital lambda. The Greek capital lambda is a symbol for the famous, or perhaps infamous, cosmological constant. This cosmological constant we have also mentioned several times on the channel. Well, it has a checkered history. It goes back to the year 1917, when Einstein published his first paper on the cosmological implications of general relativity. Ooh, can we get 20 likes? In a formal mathematical sense, cosmological constant is a constant of integration resulting from Einstein's field equations, from solving those field equations, which are a set of differential equations. In addition, however, the cosmological component can be given a physical meaning. A close look at the Friedmann equation shows that adding this lambda term is equivalent to adding a new component to the universe that has a constant energy density. Thus, any component of the universe whose energy density is constant with time will play the part of a cosmological constant. One such component is the vacuum energy. In quantum physics, a vacuum is not a sterile void. The Heisenberg uncertainty principle allows particle-antiparticle pairs to spontaneously appear and then annihilate in an otherwise empty space. Just as there is an energy density U associated with real particles, there is an energy density U vac associated with the virtual particles and antiparticles. The vacuum energy density U vac is a small-scale quantum effect that is unaffected by the large-scale expansion of the universe, and hence U vac remains constant as the universe expands. Unfortunately, quantum field theory cannot tell us the expected numerical value of U vac. So then we can rewrite Feynman equation in terms of the energy density of the universe and whatnot. We also include energy density U lambda. And then radiation density UR is the energy density contributed by relativistic particles such as photons, and the matter density. So remember we talked about some densities earlier as well from the cosmology textbook that we're using, but here's the astronomy way of seeing it. The matter density is the energy density contributed by non-relativistic particles such as protons, neutrons, electrons, and WIMPs. WIMP being the candidate for dark matter. For non-relativistic particles, is going to be rho m times c squared. Finally, the lambda density, aka the vacuum density, is the constant energy density provided by the cosmological constant. The fact that our universe is flat or very close to it means that the total energy density is equal to the critical energy density as well. Did you know? So for perfect flatness, we would require UR to be UR plus plus U lambda equal to UC, where UC is the critical energy density, and the Hubble parameter is currently at 70 kilometers per second per megaparsec. So remember we talked about the Hubble rate at one point for the expansion of the universe, and then there's the Hubble parameter. That's currently H naught equal to 70 kilometers per second per megaparsecs, which translates to a current critical density of 5200 MeV per meter cubed. This is one of the more fascinating results of general relativity because the universe is flat on large scales. We know the average density of the universe, the average energy density of the universe. Even if we don't know how much is contributed by each component, we know that the total must come to 5200 MeV per meter cubed. Since the critical density is vital to an understanding of the curvature and expansion of the universe, cosmologists frequently express the energy density of the universe in terms of the dimensionless density parameter, which is omega over omega, which is U over UC. In this case, we've talked about some omegas in the other book. And if omega is less than 1, the universe is negatively curved. If omega is greater than 1, the universe is positively curved. Saying the universe is flat is basically saying omega equals to 1, which is the critical energy density being the current energy density. By extension, we can write down a density parameter for each component of the universe. One for radiation, one for matter, one for lambda, or the cosmological constant. Knowing how the universe expands with time requires knowing how much energy density is in radiation, matter, and the cosmological constant today, and knowing how the energy density of radiation and matter evolves with time as well. So there are various exotic cosmologies that contain other components, like cosmic strings and domain walls and various types of dark energy. But for simplicity, we'll stick to a universe with just radiation, non-relativistic matter, and a cosmological constant. And this was the math / all the variables for that. We can always go over this again if this was a little quick. Hey, that's so cool. And yeah, so this was the book we just used. We looked at some cosmology type of discussions from this book, which is basically review to what we've done before when we talked about cosmic inventory and cosmology and things like that. I thought I'll give you a little bit of a review from this book as well, and always good to verify and look at things from different resources. So that's the topic that we wanted to cover today. Thank you so much for joining, and we will see you in the next